Okay, so I said yesterday we did the linear equation solver and studied its applications. And today we'll do another quantum algorithm, very different from the one that I talked about yesterday. It's related to optimization. So I'll explain a little why optimization is important to machine learning other areas, but I'm going to try to give you an idea of how quantum computers of this type work. So I'll start off by explaining optimization, and we'll work our way to the quantum machine that does the job. So here we're going to consider optimization problems, and then I wrote mathematically what an optimization problem is. Here I'm defining what's known as the continuous optimization problem, and later I'll give you clarity on combinatorial optimization, which is the particular goal in these algorithms. So this is just a mathematical definition of optimization. Just consider a function f of x. X, the variable can be called states. And so for every state in the system, in this case, you can see that x is represented, it's a two-dimensional variable, a vector if you like, with x1 and x2. And then there's an evaluation. This can be called a fitness, or I tend to think of it as a fitness function. How good or bad is that state? So in the optimization language, every point on this plane represents a state, and then we evaluate how good the state is. And the state can be very good or very bad. Typically, we formulate the problem as a minimization. Sometimes it's written as a maximization, just trivial. We put a minus sign in front. So if we want to minimize, then that deep valley is the optimal state. This peak, red peak, is the worst state. And in between, you can see there are some regions where you get a local minimum, local maxima, and other things can happen. There can be saddle points where it goes down here, up here. In the language of optimization theory, these are often called traps. Most optimization methods that are used are built around believing that there's only one minimum, so it ignores traps. And the problem of trying to find minima where there's multiple local minima and traps in the system is a very important problem. And there's ways to solve it, and I'll go into it. But essentially, this is the optimization problem, find the minimum. In the continuous case, x, you could think of as real numbers. So every real value x is allowed as a state. But on computers, of course, we don't have real numbers. And so it's much better to discretize it. And then what happens is the set of states is just over a finite lattice or a finite mesh. So there's a finite number of those. And then certain techniques can be used. Okay, so that's the idea of the optimization problem. Then this is combinatorial optimization. So, let me explain. I didn't go into enough. Okay, so we're minimizing the function. And then we have a set of inequalities and a set of equalities. And so the idea is that that function is subject to a set of constraints. So when you have all the values of x, all the states of the system, the states have to satisfy various conditions. So it might be that another function, g1 of x, for each state has to be negative or 0. And there's another function that might have to be negative or 0, and so on. And other ones might be equalities that have to hold. And so this makes the problem constrained. If these don't apply, if this set is null, there's none of these, then it's an unconstrained optimization problem. And then it's well known. If there are no constraints, then you can assume there's just one local minimum, and then approaches that are called greedy work. If constraints apply, the more of these constraints, the more you get traps in your system. So you can kind of look at it and say, more of these implies harder methods to optimize. Okay, so that's constrained optimization. And then the combinatorial optimization, it says find an optimum from a finite set of feasible solutions. So let me go back. The idea is that some values of x don't satisfy one of these conditions. They're called not feasible. So any value x that doesn't satisfy it is infeasible, Then we make a list of feasible conditions, and then we optimize. So here we find the optimum from a finite set of feasible conditions. So what happens is we make a mesh with a finite number of valid states. Okay, then the methods almost always are search algorithms. So the way that we optimize is we search for solutions. So I tend to use the term agents. So you can think of a single agent starting somewhere, and then it's walking around the system, trying different states that are feasible and looking for the value X that gives that. So it's one agent searching. In swarm type problems, collective or swarm, then you can have multiple agents that are all searching and they can talk to each other. So you can have one agent. You could parallelize to have many single agents. If anybody uses MATLAB, there's multi-start that does that. And then collective approaches, they communicate with each other. There's genetic algorithms approaches, many ways to do it. Okay, so the approaches are search algorithms. So when we want to optimize, we want to look for a way to search the system. There's no guarantee it solves it efficiently. Should be efficiently, yeah, sorry for the typo. The should be efficient searches. They're not, generally they're not. So you can't expect to have an efficient search. So this is interesting. It makes optimization is computationally hard. That's why no matter how good computers get, forever there'll be jobs for people who need to optimize because we believe that they're not efficiently solvable. So it seems to take a human being to get insight into the problem to look for shortcuts. These are heuristics. Okay, and where does it come in? Well, the applications exist in machine learning, auctioning, operations research. So this is analytics, intelligent decision making. Basically, optimization underpins a lot of algorithmic development and many others. So optimization is widely useful. There are many universities with many departments that are focused entirely on optimization. So it's a giant field of applied mathematical research. Okay, any questions so far? So this is a problem we want to tackle and see how a quantum computer can help. So I won't get to the quantum for a little while. I'm going to set the stage for the problem. So the one I want to talk about is simulated annealing. Historically, simulated annealing, so many of these optimization routines come out of observing something in nature, seeing how nature behaves and getting an idea. Annealing goes back 7,000 years in making metal. You bend metal, make it. And so the idea is that you take a metal that's got some structure to it, then you apply heat and move it to different shapes. And so the term simulated annealing really comes from metallurgy and the ability to manipulate, heat things and then cool them into different shapes. So that's the origin of the term. Simulated means on a computer. Simulated annealing is one approach to optimization, and the approach these approaches are known as meta-heuristics. So a heuristic is, I tend to think of as a shortcut that you're doing something and you realize that your problem is specific in a way, you can find some way to simplify it. A meta-heuristic, meta is Greek, it means it goes beyond a heuristic. And so a meta-heuristic, I wrote down in blue here what it is. Meta-heuristics are strategies to search for the best solution in a way that you don't care about the problem. So you might have simulated annealing or genetic algorithms or steepest descent or hill climbing, various ways to do it. And each of those, the ideas doesn't depend on the problem. It goes beyond that. And the idea is to guide search procedures. So it's a way, the meta-heuristic gives a way of searching this space. And the idea is, with the meta-heuristics, is to try to get the global optimum. Computers are always approximating, so it approximates the global optimum. I'll mention soon approximating the global optimum and finding the actual global optimum can be different complexity classes in computing. So you have to be very careful here. You have to be very careful how you decide how good an approximation is with the size of the system. And then meta-heuristics include simulated annealing. evolutionary algorithms that to me include genetic algorithms, differential evolution, and so on. I didn't mention, but swarm optimization techniques, collective intelligence, and also local searches, which are the most common. So if you're a MATLAB user and use multi-start, it'll just try to find the best local searches. Those are all meta-heuristics. Does that make sense? And then what we're going to focus on is the simulated annealing meta-heuristic, which is the one that seems quantum might help us. Okay, so this gives you an idea of how simulated annealing works. And the idea, I'll just go back to this slide for a moment. You start somewhere. Remember, so the search is supposed to find that point, the minimum. And so somehow it's going to search to find the point. It could go straight downhill, but if it started somewhere else, it might have some uphill to get through to go downhill. So in this simpler picture, it starts somewhere, and here's the target. It needs to find that place. How's it going to get there? Well, if you use a greedy algorithm, the greedy algorithm only looks locally, and if this goes up and this goes down, it will just go down. It looks for the minimum. And it will go down, 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 and then a greedy algorithm will stop here, because if it goes in if it moves away from it, it gets a worse solution. So that's the problem. Greedy algorithms are very fast and very efficient, and when they work, typically with people who optimize, they'll use these greedy algorithms and then only switch to a different meta-heuristic if greedy is not delivering. So then the question is, what do you do when the system gets down to that minimum and then it's got to go beyond? Well, what you'd like to do in this slide, it says hill climbing, you'd like to somehow perturb it so that if this is not a big barrier, it can just climb over and then it drops in the next one. You want it to climb over. When it gets to here, it won't have enough energy to climb out. That's the intuition of simulated annealing. So how does it get the energy? Well, so let me tell you physically, and then I'll tell you computationally. So physically, you can imagine that if you keep it hot, something hot will jiggle around. So if it's a hot system and the particle winds up in that minimum and it's very hot, it's got some probability from the jiggling that it will cross the boundary. So so initially in simulated annealing, you somehow want to keep your system hot so that it will jump over these barriers. But if it's too hot, it'll jump out of this. And so you want to keep it not too hot, and then eventually you want to keep making it colder and colder until finally it's cold enough that wherever it is, it will just sit there. This is known as cooling in simulated annealing, and the time scale and how it's cooled is actually really critical and not well understood. That will come up in our quantum machine. So the cooling process is very important. Okay, now let me tell you computationally what it means to cool. Yeah.
How would you know that you are at a local minima, not at a global?
You don't know.
So if you're heating it, so it will come up, and you are at a global one, then you climb up.
Yeah, if it's too hot. That's right. That's what I was saying. Cooling is very tricky, and it's not well known how to do it. So the intuition is that I'll just call it an agent. So the agent gets here. If it's hot, it can escape. If it's cold, it can't escape. Same here. But if it's too hot, it will escape from where you want it to be. So obviously, how hot the system is vital, but you don't know the answer. So there's no guarantee when you do it, it's going to work.
Pretty simple intuition be to look at the distance it has from the point it started from, the point where it started going downwards from, and to see how to basically roll that far up from the right side, and if it ends up hitting that threshold, it will go back down and just rest.
So you're assuming you know what this is, right? The function.
No, looking at how far down it goes.
How do you know how far down it went?
As it was going down, it keeps going down until it reaches a point where it's up in both sides. Then looks at how far up it was before and the distance between.
Okay, so let me cut it short. I mean, this information is not given. So there's no way to measure distance or to know how far down. You have an unknown. So the intuition is you generically think of this kind of pattern, and then cool it to make it go to where it should go. But you can't measure to know if it's there. So that's the problem. This is done. It's not a rigorous theory. It's just, it's again, a meta-heuristic. It's just used. So the point is valid that you don't have a way of knowing. In all these systems, you just, in the end, you only get something good enough. And then you need to, unless you search everything, map it out, which is generally not feasible, you just run your simulated annealing until you're satisfied.
Maybe you should mention that you have to do it many times and then take the best answer.
Yeah, so this is single agent. Yeah, so what Abdullah is saying is correct, that you, I mean, typically when you do it, you might not be satisfied the first time. You might take multiple runs, do a single agent, and do it again and again to get an answer. See where it winds up. That's the idea behind it. Okay, now let me tell you what the temperature is computationally. So the way to think about it, remember I said we'll do it discretely? So instead of thinking of a real number value along the axis, we can think of it as being a lattice, so different points. So when it's here, there'd be a point that's a neighbor here and a point that's a neighbor here. And then here, the trick is it has to accept becoming replaced. The state has to update to a new state, a neighbor, that's worse. So the computational meaning of temperature is the probability that will accept a worse value. What makes a value worse? Well, this is an energy. Think of this as an energy axis, and it's trying to find the minimum energy. So in a greedy algorithm, it will always go to where the energy is lower. In a global algorithm, it will, well, in the simulated annealing, it will accept going to a neighbor that's worse. And then temperature in physics, if you take temperature in Kelvin multiplied by Boltzmann's constant, it's an energy. So the temperature multiplied by Boltzmann's constant is an energy. It will accept a neighbor that has higher energy, provided the higher energy is lower than the energy associated with the temperature. Okay? So the way to think about temperature computationally is that it's a probability for the agent to move to a higher energy. And then when you cool the system, as the system gets cooler, it means the probability of going up to some fixed energy amount gets lower and lower. So eventually, when you've cooled the system completely, it will not accept any neighbor that's higher energy. Does that make sense? Okay, so that's the concept of simulated annealing. Okay, now that's what I hinted at. I prepared a slide on the cooling schedule. And so just to recap, the temperature T corresponds to the probability of accepting jumps to worse neighboring states. It's all discrete. Now the next thing is that the cooling has to be done slowly. So you can kind of think of the agent jiggling around. It needs to equilibrate. And so the cooling has to be done slowly in order to allow near equilibrium dynamics. Not rigorously proven, but the idea is it must be able to do it. And I say it depends on the topography and the present temperature T, which means that you have to actually, you don't know, I'm going to call this a landscape. So you don't know the landscape, but steep jumps like that and shallow jumps contribute to different needs for cooling. So the unknown topography of your system, the layout of the landscape, is vital in working out the time scale to cool, and yet you don't know the time scale to cool. So that's a critical point. So there's people doing research their whole lives just on how to cool the system, how to do proper cooling. And it's generally empirical. They'll take problems, try to solve them, see what happens, and then adjust the cooling dynamics accordingly. And then there's a couple of main directions in cooling. One is adaptive, and so it's, cool a bit, measure, this goes back to the measurement concept, see what you get, and then adjust the cooling accordingly. Or you could do it more like a physicist and take into account thermodynamic principles. So then you use thermodynamics and cool according to thermodynamics. So those are the two main directions, adapting based on measuring or taking a thermodynamic perspective. And the thermodynamic perspective is about keeping it in thermodynamics, we have equilibrium and non-equilibrium thermodynamics. So the idea is to try to keep it close to equilibrium according to fundamental principles. And then in the end, you just hope that it's going to work. And then there's also usually built into one of the algorithms is an abort strategy. So at some point, after your best intentions and best approach, it could be going badly. So at some point, the algorithm might abort, just stop and give up, and then restart. So there's a restart built into these. All of these problems carry forward into the quantum domain. So we do quantum annealing approaches to optimization. These all matter. Okay, so let's go to quantum annealing. And so quantum annealing is not more rigorous than simulated annealing. There's no proof of it. There's just an intuition. I'll tell you what the intuition is, and this is what drives people to do research in the field and build machines, is to try to make use of quantum mechanics in the following way. So over here we have that landscape again, and then, as I explained, there's a thermal jump. So what happens is, again, explaining, that you have some temperature, and the temperature, as I explained, gives the probability of accepting a jump that increases energy, and it's improbable to jump higher than the temperature. So the agent can jump over barriers to finding the minimum. But if you take this diagram really seriously, so if you know quantum mechanics, you'd say, well, you could think of this like an energy potential function. And then if you think of the agent as a localized wave packet, then the agent can tunnel through a tall, thin barrier. And so the concept is that if we build a machine that's quantum mechanical, then in addition to the thermal jumps, tall, thin barriers, so the tunneling time goes as the area under the barrier, so it's the height times the width. So a high barrier with a narrow width has a small area. The small area allows, gives a reasonable probability for a quantum tunneling event. That's about as deep as it goes in my view of the field, is that it's really this intuition that motivates the research. Okay? So you get the idea that we're augmenting a thermal jump to get to the minimum with a quantum tunneling event. That's the concept. Then we build the machine and hope that it works. And then the other question, and this is what people look for in the field, is if the intuition holds, then the question is, where are the problems that would have these kinds of events? So these kinds of features. So there's a search on for the kind of problem that would deliver this feature and then enable quantum tunneling to help. Okay, and then also for quantum annealing, we formulate combinatorial optimization problems. And I'll explain more how the combinatorial optimization problem connects with the physics and the Hamiltonian that we talked about, went through the problem this morning. Okay, any questions at this point?
Yeah, probably. This seems like you can look that far out and that far ahead.
No, it goes back to his question too, that we're saying if the problem exists of that type, this would help, but we're not assuming we know a priori its nature.
No, I'm not even talking about the nature of the problem. You've got a cross landscape, right? And you've got that tall thing outcrop right away. And okay, you can only determine that it's a tall and thin outcrop if you can look past the outcrop, and you can look how high it is and how thin it is. And you don't have a non-local view.
But that's what I'm saying. We don't know.
You don't know.
No, you and I are agreeing. I'm saying there's no a priori knowledge.
Yeah, there is no outcrop. So,
But what are we discussing?
how do you then tunnel through anything like that?
Well, the idea is that there's a problem. It might be of that type. We just don't know it.
You just don't know, right?
So then, thanks for the opportunity to make it really clear. What I'm saying is, people are building quantum annealers. They are searching empirically for problems that could show a quantum speed up. The intuition is if the problem is of that type, then a quantum annealer could help. And they don't know in advance. So it goes back to what I said yesterday, class, that so what's happening is a lot of companies are just testing empirically. They buy time on a quantum annealer. They test their problem to see if there's a speed up, precisely because they don't know. So your point when you say we don't know it, we also don't know if it isn't. Yeah. So just giving you an honest, clear explanation of what's going on.
So just to clarify one thing, before we get to quantum annealer, the only thing we know about this is that we're stuck in that local minima to the left, and that to the right is.
So how do we know we're stuck?
Meaning we can't we haven't, as far as we can experience this, all we see is that the temperature.
Sorry, I'm lost. You said we experience. So I said I need it really precisely stated and I can answer.
Okay, so
But there's no we and no experience.
As far as I can understand,
Yeah.
we're at a point where the more right we move, the more we see that the temperature is.
So who are we? You mean the agent or the client using the system?
The agent.
The agent, and so you said the agent moves right, and what happens?
It just sees the temperature increase.
No, the agent doesn't see a temperature. The agent, all the agent knows is that if it moves right, it knows the new state. So there's a new state, and there's an energy difference for the state, and it flips a coin. And the coin is weighted according to the temperature as a probability. Then there's a decision. So if it comes up heads, it moves. Comes up tails, it doesn't. And the coin is biased by the temperature. So it doesn't know the temperature. It has a biased coin to flip. Okay, go ahead. I'm just clarifying as you go.
Okay, so what we're looking for is a state of the lowest temperature, right?
We is now the client?
Yes.
Okay. We are not looking for a state of lowest temperature. The algorithm runs and cools, and at the end of the cooling schedule, the agent, if everything went well, the agent is then residing at the local minimum.
Right.
So then we, as the client, get the answer back, and the answer is the state of the agent.
Right.
That's the return in the code.
Right. I guess I misunderstood correctly.
No, it's okay. It's good to be able to clarify. So that's what's going on. The return in the code is the agent state. Good? Any other questions? Okay, so that's the intuition. I hope it's clear now that, that as we're getting out, that there's no guarantee any problem is of that type. There's no guarantee that the problem is of the type it will work, that the testing is done empirically. This is why companies are doing what's called hybrid quantum algorithms. They take the algorithm, make parts of it fit the annealing, plug it into a commercial computer like D-Wave, and then benchmark. They just see how it performs, and the idea is to know whether there's a quantum advantage or not. Okay. And better need to be clear too, because a lot of times in quantum computing we talk about speed up. Nowadays, the better, sometimes they talk about accuracy. So the question is not whether it's faster, they don't care if it's slower, whether it will deliver a superior result, a superior optimal result. Okay, so let's talk about the Hamiltonian. This one I captured the Hamiltonian, I hope it's readable, that I just copied, took an image off the D-Wave website to get it right. And then I'll talk about this Hamiltonian in light of what we discussed earlier. So let me explain what the strategy is, and I'll use the board to explain some of it. So the idea is, and so the idea is to construct a Hamiltonian that encodes the problem. And I'll explain in a few minutes about satisfiability problems, so how a problem is encoded. But at the moment, don't worry about that. There's some Hamiltonian that represents, whose ground state, lowest energy state, is the solution to the problem. And there's another Hamiltonian H naught, which is a Hamiltonian that has a ground state that's easy to prepare. And then the idea is to evolve the system so that the Hamiltonian that governs the dynamics begins here and ends here, and evolves slowly according to a schedule. And then the new state will be the answer to the problem, and it's read out. Okay, so let me explain, and I hope things are visible to you. So I said yesterday about the idea of the magnet. So just going back to that picture, we have a magnet, and then just to be simple, I'm going to use this means it points out, and this means it points in. And this will be magnets, so it's just tiny magnets. Okay, so that's what we're going to build. It's a two-dimensional, like just to take seriously the idea of the magnet, build it. This is what D-Wave has done. They're flux qubits or magnets. So it's a very good analogy. Then what happens is we just set it up. So we can think of the magnets as pointing in or out, right, and keep going. And so on. And so on, right, and keep going down. Get the idea? So it's just a set of magnets. They can point in or out, and it's in some system. And then the idea here is that the problem Hamiltonian is set up so that the lowest energy of this magnet is the one, so like if this could be R0, and this could be R1. So the idea is to create some Hamiltonian, which is essentially just little magnets at every point that will control the whether the magnet is pointing in or out, and the coupling strength between the neighbors. So it controls all that, and in the end, the resultant magnet has magnets pointing in or out. You read them as zeros and ones, and the string of zeros and ones is the answer to your problem. That's how it works. The initial state, typically, so this is the final state, the problem, and this is the problem. The ground state, I'll put down the ground. So this is, ground means lowest energy. Energy state for the problem Hamiltonian. And then here we have the ground state of H0. Can you see it over here? Is it visible? Too much glare. Does it help if we shut off the front lights to? It does. Okay, can you see it better? Okay, good. All right, you got to complain, or I don't know you can't see.
Somebody mentioned it at the very start of class, but nobody heard him. So
what?
Somebody actually mentioned it at the very start of the session.
To me.
Basically, he just said it out.
Somebody says at the start of every session?
No, he said it in the start of this session.
Okay. Who? And I didn't hear? Got it. Thanks. Okay. So then what happens, the ground state of this one would just be completely magnetized. Okay, so you might start off like that. The magnet starts off with all the spins pointed one way. That's what we call a magnet, right? So you just prepare it as a magnet and then apply local controls to be able to produce that string. Okay, so the trick then, and I'll show you how to do it, the trick is how do you take a problem, so a combinatorial optimization problem, and write it so that the lowest energy state of a Hamiltonian is the answer that you want. And I won't go through all the details, I'll just sketch so you got an idea of how to do it. Okay, so that's what we want to do. And then the idea is that we have to go from this Hamiltonian to this one, and there's going to be some schedule, like we do for simulated annealing, but now it's not a cooling schedule, it's just a schedule. Okay, start here and evolve to here, and it will have to go slowly. So as I said before with simulated annealing, deciding slowly typically is either an adaptive approach or it's a thermodynamic principles approach. Here I'll tell you what it is. In fact, I wrote it here. Cooling is slow, I shouldn't have said cooling, just the schedule is slow compared to the spectral gap. So let me explain what's going on. So that evolution has to be slow, and the slowness comes out of the Adiabatic Theorem. So see, I know a lot of you are computer scientists, so I'm sure you don't know that, but there's something known as the Adiabatic Theorem. Does anybody know it here? No, nobody? Okay, so let me try to explain a little bit. So we remember that the Hamiltonian H, so Hamiltonian H has eigenstates. So I'm just going to write down the following. So the idea here is that this is the Hamiltonian operator, and the operator can be written as a matrix. And then this is an eigenstate. And the eigenstate is an energy eigenstate because the Hamiltonian represents the energy of the system. And over here, this is the eigenvalue for that state, and that's an energy eigenvalue. So we have our Hamiltonian, and we can diagonalize. So this is obtained by diagonalizing. And if we diagonalize the Hamiltonian operator, then it represents different energies. And because it's quantum mechanical, it can be in a superposition. Classically, it's a fixed energy. Quantum mechanically, we can have different states of energy all in a superposition. But those are the energy states. Now what happens is we make our Hamiltonian equal to, and then I'll write down A of S H naught plus B of S HP. So this S is T over T total. T total. And then what's going on here is this is time, real time in the system, it's like the cooling schedule. And this is the total scheduling time. Okay, so we're going to, I'll replace this by H of S. So there's going to be a slow evolution. We start off here, and the system is cold, so it's a magnet. All the spins pointed the same way. Then we change it slowly by applying different controls, and then the result is that the new ground state, that this is eventually shut off. So you can imagine that if you did a plot, S, and then here is A and B, you start off with A very big and B off. So this would be your A, and this would be your B, is one idea. So you just start off, initially this is on, and then the system is a magnet, and then it evolves until that's off and this is on, and you got the solution. And that's S, and it evolves out to some final time. And it's same kind of thing. It's actually hopeful in the sense that simulated annealing is hopeful. So in the early days, people thought they had very good proofs of it. The proofs weren't perfect, and so there's a lot of speculation and conjecture in the area. So that's the idea. We've got to make the system evolve in that way. Now, the Adiabatic Theorem tells us the following. So the Adiabatic Theorem tells us that if H of S evolves slowly, then, and we have to be careful here, then the eigenstate, which is now time dependent, evolves slowly. And what it tells us is that an eigenstate evolves as an eigenstate. Is that visible? So as an eigenstate. And then most importantly is that the ground state remains a ground state. So let's go back to here. What could go wrong? Over here, we start off with a magnet, all spins out, and then we come up with the other solution. But as it goes from there to there, it must get excited, right? So if I change to that, it's no longer a ground state. So as I'm changing my system, I can accidentally cause an excitation, and then it's not in the ground state. So the concept is that this is forbidden if it's slow enough, okay? And that's built into the Adiabatic Theorem, that, you know, if we evolve slowly enough, then there's a ground state. And what is slowly enough? Well, the answer is that we would, if we diagonalize the Hamiltonian and we look at the energy values, that's the spectrum, then the separation between the lowest energy and the next lowest energy is a gap. And the energy and time are proportional. So if you know the energy gap, then you know the frequency gap. Frequency is a rate, and so it tells you how slowly to move. So basically, the idea is that you have to evolve slowly compared to the gap between the lowest and next lowest energy. The problem, there's a lot of problems with that. That proof is not airtight. It turns out that that's necessary but not sufficient. So it has to go slowly enough. I should be careful. It actually turns out it's not necessary nor sufficient. But there's a lot of assumptions that people build in to make these arguments. And so they say, this is how slowly it has to go. What I'm telling you is that even if they satisfy the condition, it's no guarantee that it will work. Okay, so the idea then is that we want to control that evolution. Let's look at this Hamiltonian and tie it with what we did this morning and yesterday. So can you read it? Is it okay? No?
Could you tell us what is sigma z in the second term?
I can tell you it's a sigma z. Here? Yeah, let me, how do I control the lights? Okay, so I just want to turn off another and see if it's, okay, let me make it darker until you tell me you can read it or I give up. It's a lot of light switches.
We don't have any lights.
Yeah, that's right. Is it getting better?
Actually, it is
Getting worse?
not worse, same.
Okay, so it's unfixable. Okay, so I'll abort this code. All right, good. Okay, I turned on a bunch more switches I lost. All right, pardon me? I can't hear you. Yeah, but I can't do any better, so I'm gonna, what? I can't, yeah, that's what I'm getting at. Okay, let me go through it. I'll just tell you what it says, and then I'll write what I need to write. So it's Hamiltonian, that says Ising. Ising, the Hamiltonian is named after Ising. In fact, it was Ising's supervisor who suggested. So Ising wrote it down. His supervisor suggested the problem, and then his supervisor kindly gave Ising all the credit. So it's known as the Ising Hamiltonian. Then there's an equal sign here. This is A of S, which is the A of S I wrote over there. Over 2, we don't worry about the over 2. This is the sum over I of sigma xi. So that's the Pauli operator, the x, and the eigenstates of x, in this case, are in and out of the board. So that's what's going on here. So if we shut off that and just do that, the lowest energy state is all the spins pointing out. That's the lowest energy state of this Hamiltonian. Does that make sense so far? No? Doesn't look like it makes sense. Okay. So in this case, the H naught equals the sum of, and I'll just write it as the Pauli operator x, I. Okay. So what are the eigenstates of x? X of 0 is 1. X of 1 is 0. So what would be the eigenstate of x? Okay, let's say we did x of 0 plus 1 over root 2. Can you read that? Okay, so what is the answer? What's x of 0? X of 0 is 1. So it's 1 plus 0 over root 2, which is 0 plus 1 over root 2. You see? So that's an eigenstate. What if we did x of 0 minus 1 over root 2? What do we get? Yep. So I'll write that out. So you get 1 minus 0 over root 2 equals negative 0 minus 1 over root 2. Do you see? Okay, so that corresponds to one spin. So you can think of 0 plus 1 as the state that points into the board, and the 0 minus 1 is the state that points out. The 0 minus 1 has an energy of minus 1. The one pointing into the board has an energy of plus 1. So the energy difference is 2. So when I do that sum, it's the sum over every site in the magnet, and then the eigenstate of that sum is just the product of these states, the lowest energy states, 0 minus 1. That's what I've drawn. Does that make sense? Okay, makes sense to two people. Okay, so all we're doing here is we're writing the Hamiltonian. We're writing a simple Hamiltonian whose lowest energy state is one that we can easily prepare. So having all the spins point the same way, making it magnetic, is the easiest prepare. And the easiest way to write the ground state of a magnet is as the sum of Pauli operators. Okay. And then if up is 0 and down is 1, then right would be, well, out of the board, in this case, is 0 minus 1 over root 2, and into the board is the opposite. Right? So you get it? It's 0, 1. Out of the board is 0 minus 1. Into the board is 0 plus 1. Got it? Okay, so that's the Hamiltonian that's easy to prepare. Now, that is going to ramp down. It could be by this schedule or not, but initially, it's the ground state of that Hamiltonian, the other doesn't matter. Then we're going to let it change in some way, and the new Hamiltonian is the following. It's got two terms here. So it's got the sum of h subscript I, sigma zi. So I'll write that here as, that's saying it's the sum of h I, and then the sigma z I'll just write as z. Zi. Just like we had xi. And so that zi is doing the same thing. It's applying an energy, but the eigenstates of z are the 0 and 1. It's 0 and 1 instead of the x eigenstates, which are out of and into the board. What it's actually doing there, remember I told you about this earlier about the Hadamard tensor n was the parallelization? So the effect of this term is to do the parallelization. Instead of starting with all zeros, then it's effectively forcing a different basis. So it's saying you prepared it in all zeros in the x basis, but in the z basis, it's the superposition of every number. I did that this morning in the problem session. Okay? So that's what this term is for. And then we have this term, which is the coupling. Oh, I didn't tell you. This is a weight term also. So it says when the new Hamiltonian is on, it's in a ground state, but it's saying it'll push some values have to be low in energy, and other values with small hi don't have to be. So instead of forcing it, it's kind of making an allowance where you have minima and not so minimized. So it's it's allowing some variability in which ones have to be close to the zero eigenstate, the ground eigenstate or not. Let's go through this one then. So this is the other term, similar but easier than the one I did this morning. So that one is J, I, J. Oh no, is it? Yeah, sigma Z. Okay. So that one is the sum over I and J. So those are labels for two sites. And then we write J, I, J, and I'll not use sigma, I'll just write it as a Z. So we've got Zi, Zj. So remember this morning we did the sigma dot sigma? Here we don't have to, right? So let's just understand what that is. This would be, so if we thought about one dimension, let me talk about one dimension first. Then if we talk about one dimension, we can think of the line, and then we can imagine our qubits on the line. And then let's say that this is the ith term, and that's the jth term. So what we would do, that operator is the identity twice for that. Then we take Zi, then we take the identity twice again. Then we take the j term, and then we take an identity for that. Do you see? And remember we went through this morning and multiplied these things out? So based on what we did this morning, you get the idea that we're multiplying. So that sum represents that operator if they're apart. And then what happens is these two are interacting by a strength of Jij. Okay, so that's what happens. And then we pick a different pair, we get a different interaction strength, and then of course we actually do it in 2 dimensions. You know, so we might generalize it, and then we might have the jth term here and the ith term here, and an interaction between them, and write out the full thing. So that's what's going on. And then what happens in the experiment is they control these things. So they essentially what they do, and this is in the D-wave system and others, they just build little magnets at each site and little magnets between, and they're able to, and the way you make a magnet is you set an electric current. So electric current goes around in a circle, it generates magnetic flux, and so it's these tiny superconducting electrical currents located around, and the whole purpose is that those are tuning these parameters and changing over time. That's what they build. Okay, and the ground state of this, if this changes slowly, you prepare in the ground state, you end up with the ground state of that. That ground state is over here, and that's the answer to your computational problem. So far, so good? Okay, then let's go on. So, oh, there it is. See if I covered all that. So we have the Hamiltonian. We know it has to be modified slowly, and you get that. Okay. So now I want to tell you about what the problem is. So what does it mean to encode a problem inside of the problem Hamiltonian? And for this, it turns out that this Hamiltonian coupling is very much related to computer science, what's known as the satisfiability problem. We've got computer scientists here. How many of you know the satisfiability problem? Yeah, it's a good number. Okay, excellent. So the idea is then we need to formulate a satisfiability problem. Not everybody knows it, so I'll just give you a brief rundown of how it works. So the idea of a Boolean satisfiability problem is that we start off with binary variables. So we can think of x1, x2, x3, and so on. And every value of these xi's can be 0 or 1. And then we could go from variables to what are called literals, and literals include the negation. So we can take x1 as a Boolean variable, and then if I put a not in front, it negates it. So this is the combination well, if I write x2 or not x1, I can call them literals if it includes the variable and negation of a variable. Then we are allowed to apply logical operations. And logical operations and, or, and not. The parentheses are just ways of grouping. So whenever we put parentheses around it, this is called a clause. The same as a clause in grammar for a sentence. So here's a clause. This clause has two literals, x1 and the negation of x2. This clause has three literals. This clause has one literal. And then this forms a statement. And then the statement can be true if so the statement is said to be true if there exists an assignment to x1 and x2, x1, x2, and x3, so that this statement evaluates to true. Okay, so if 0 is true and 1 is false, well, okay, I don't care. All I need to say is, like, if I apply 0, 0, if I apply x1, x2, x3, and I assign them, let's say, all zeros, will it evaluate to true? Anybody up to actually doing that now? Make sure you know. So let's say that x1 is 0 and x2 is 0, and this is an OR. So that evaluates to 1. Okay. What does this evaluate to? So x3, what do you want it to be? 1. Okay. So we have x1 and x2 were both 0, right? No? Sorry, I forgot what I said. No, x1 is 0, x2 is 0. Yeah, but let's just assign first. x1 is 0, x2 is 0, x3 is 1. Okay, let's go through it. So just double check. What do you get? 1. For this? Okay, so this clause is 1, this clause is 1, this clause is 1. And then when we do the AND operations, what does 1? Okay, and do we call that true? If 0 is false and 1 is true, then it evaluates. Yeah, we have a choice. Okay, so you see, then we evaluate the statement, see if it's true or not. So this is what these satisfiability problems are, is whether there exists an assignment of x1, x2, x3 in this case that evaluates to true. And writing it with clauses that have ands between them, this is known as the conjunctive normal form. So if we make all our clauses with ors and clauses are joined by ands, then it allows us a nice structure to, kind of like a syntax for how to construct statements. Turns out that every Boolean function can be expressed in conjunctive normal form, and that allows us a way to compare. And then there's a more restrictive form of this that's known as ksat. And ksat says that there are k literals per clause. Every clause has k literals. Okay, and I wrote the case of 3sat here. And 3sat is the case that every clause has 3 literals, exactly. Now, it turns out that if we did 2sat, everything is just 2 literals, it turns out to be efficiently solvable. What do I mean by efficiently solvable? I mean that the cost of determining whether there's an assignment for the variables that evaluates true grows polynomially with the number of clauses. 3sat doesn't have that property. And 3sat is actually famous because it's tied with the Cook-Levin theorem. And the Cook-Levin theorem proved 3sat was NP-complete. So we had these complexity classes yesterday. 3sat is NP-complete, and it's the canonical case of NP-complete. So a lot of times when you prove NP-complete, you map it over to a 3sat problem. Okay, and that's very interesting because up to 2sat is efficient, 3sat's not. The optimization problems are as hard or harder than these, and so that makes an optimization can be mapped into this form, and so the result of knowing that this is NP-complete is that you can then show that optimization problems are NP-hard. So at the beginning, when I told you optimization problems are hard, and so people will be working forever looking for heuristics to make it efficient, is made rigorous through using 3-sat and the Cook-Levin theorem. Okay, so that's the issue. What's important for us, so what's important is that we can map optimization problems to Boolean satisfiability problems, and we can connect these to the physics of the magnet. So the idea is that instead of writing a code on a computer that will try to do optimization, can we build a machine that will have physical elements representing each variable, and then these become interactions between the elements, and these become higher order interactions between groups of elements in a way that our physical machine is trying to solve that. Okay? If you get that point, you get everything, because the whole idea is to build a machine that does it. Now, we don't build a classical machine to do it because we don't expect it to be any better than doing it on a universal computer. So we don't see the advantage. That goes back to what I told you yesterday about the embeddability in reversible computing. You know, that you can take Boolean logic, embed it in reversible logic, which turns into permutations, but you discover through an isomorphism there's no advantage. That's why that field never grew. But in the quantum world, we know that sometimes quantum gives an improvement, right? Believed in the case of factorization and proven in the case of search, Grover search. So in this case, this is where the optimism comes in, is you say, well, if we build a machine that solves a satisfiability problem and it operates by quantum principles, maybe it will deliver an advantage. Okay, so I'm giving you a really honest statement so you understand what's going on. Is it clear? Can't remember what I said. I wasn't listening. Yeah, I'm saying that if we can build a machine that physically simulates the satisfiability problem so it evolves to get the true statement would become the lowest energy state. If we can build a machine that does it and it operates by quantum principles, so it's not governed by the Boolean logical principles, then maybe it can perform better than a classical computer running an algorithm to solve it. So,
do you mean physical here as a form of concrete?
Yeah, this magnet. That's what I'm going to get to. So we're creating a magnet. So we're hoping that by making the right kind of magnet that we can control on a microscopic level to represent a satisfiability problem, and then we hope that because it's governed by the laws of quantum mechanics, it could deliver a result that makes it easier to solve in some way. That's it. But it's really not a rigorous statement. It's just an aspiration. Does that make sense? You look like aspiration. Aspire is what you hope for. Aspiration is a hope. Sorry. Pardon me? Might be and might not be. And then the question is, I mean, this is what goes back to you. If you're using these kinds, if you're doing optimization in your life, then the question that comes to you, what comes to companies, is saying it might or it might not hold. You have two choices. You can ignore it, and then if it ever works, you can use it. Or, and this is the case with a lot of big companies, they don't want to discover that their competitor found an advantage and they didn't find it. And so in the business world, they need to know in advance.
Just a clarification for myself. So in the classical model, we would say all NP-complete problems are polynomially equivalent. So just solve one of them, and if you can solve one of them efficiently, you're done. Now here we are having this additional clause of physically simulate this specific NP-complete problem. Does this polynomial reducibility from classical still hold when we have this physical simulation or physical realization requirement? Could it be that one NP-complete problem does admit this nice physical simulation or realization, while some other problem may not because of some additional physical restriction that comes in for that specific problem?
Well, okay, so let me tell you, there's a couple things to throw in. One is in the community that aspires to make use of this, like way back 18 years ago, MIT, Farhi, Goldstone, et cetera, their first papers argued that they kind of argued for a complexity advantage. So the idea is that NP-complete if you read it and you think about what they say, it's almost like they're trying to say NP complete would go to BQP, which they don't say. Nobody says that anymore. So the idea that it's NP complete wouldn't be modified by this. The argument that they'll say is something like, if it turns out to be exponentially expensive to simulate, the quantum annealer might also be exponential, but with a better exponent. See? So then the idea is they don't argue for a change in the complexity of the system. There's another subtlety here that I think you know. It's that when you go from this and you, like if you take the ground state problem and you map it to the quantum domain, you go from NP to QMA, right? You know this. So there's a, because of the QMA hardness for ground states of Hamiltonians that turn into the quantum version of the satisfiability problem, it's more and more people believe there cannot be a complexity advantage. Does that answer the question? Okay, but you asked about the polynomial reduction. So if everything stays in NP complete, I think those all hold. Any other questions on that? Okay, so that's the satisfiability problem. I'm trying to remember what I did. Yeah, that's the last slide. Okay, so this one I was still working on. That's why I was late for the photograph, trying to get the lecture ready. So I think I have enough to say. Okay, so what I want to say here is we have the task of, this is the satisfiability problem in computer science. It's got a good structure. It's used for various proofs. This is the physical Hamiltonian describing the magnet. They don't look the same. Now let me explain how to connect the two. So in this case, I wrote it here, we have these Pauli operators, okay? So in the satisfiability problem, we have literals that can have the value 0 or 1. When we map it to the quantum domain, we get an operator whose spectrum or eigenvalues can be 0 or 1. You see? So in this case, we're replacing the satisfiability problem with these literals by Pauli matrices, and instead of having two possible values, it's two possible eigenvalues. Does that make sense? So that's the replacement. It's a very straightforward replacement of that. The next thing is here we have that HI and the JIJ. Those are controllable. In the theory world, they're written as real numbers, but in all the experiments, you can't do that, so they're digitized. So like D-Wave, for example, has 4-bit control over these, so it means that there's 16 possible values of each of the numbers, and then they can tune them over discrete time steps. So what happens, the analogy with these coefficients is, imagine that you could go here and put a coefficient in front so that some clauses are more important than others. So if you could vary the weight of the clause, that becomes a weighted SAT problem. But in between, it turns out that we don't have to solve the satisfiability problem. There's a version called MaxSat. So the computer scientists in the room, do you know MaxSat? Yeah? Everybody who, most of you don't, right? Yeah, you learn it. Okay, good. Oh, that's very logical. Yeah, okay, yeah, logic, most of you don't, right. So the point here, let me just explain MaxSat. So SAT is not directly used optimization, it's MaxSat. So satisfiability asks, is there an assignment of variables such that the statement evaluates to true? MaxSat asks the question, what is the maximum number of clauses that would evaluate to true under some assignment? So you could say, you know, this product might not work, but it could be that you can find an assignment of variables so that the first 3 clauses with the AND operation between evaluate to true. So then the maximum number of clauses is at least 3. Do you follow? So we're changing the problem. Instead of saying, does there exist an assignment of variables such that evaluates to true, we can say, what is the maximum number of clauses that can evaluate to true under some assignment. So that's the max sat problem. And then the max sat problem, if we only have we do the 2 sat version, so 2 literals per clause, then we have max 2 sat. And max 2 sat relates to optimization. Now, if we made only 2 literals per clause, and we allowed a variable coefficient in front, then we're exactly at the magnet. So let me explain. This Hamiltonian, let's ignore this and just study this term. This is an operator that has eigenvalues 0 and 1, so it's the quantum version of the variable. That's another one, and then that product is the quantum version of the OR operation. Oops. So here we have ORs in between. We have 2 literals, so we just put the clause here. The sign, whether it's a plus or minus sign in front, no, I won't say that. Okay, we have the pair of variables with that operation is here, and then we have a coefficient, and that coefficient would be the weighting in front of the clause, okay? And every clause has 2 variables in the magnet. It's always 2, all the physics comes out of pairwise interaction. And so it turns out that the Hamiltonian of this type is the weighted max 2 sat. All the clauses have 2 variables. All the coefficients are tunable according to some discrete set. And then the ground state is the one that's equivalent to the maximum number of clauses evaluating to true. Not the maximum number of clauses, the sum of the weights of those clauses. So in that sense, the physics of a magnet meets the mathematics of 2 sat, weighted max 2 sat, and then we quantize the machine and hope that will help us get a better performance in solving weighted max 2 sat. So the idea is, and then when you, what is the maximum number of clauses that can be satisfied? Oh yeah, that's sat. Okay, I didn't get a chance to write it down, so I just say it to you. So let me go back to here. So the idea is that we create this machine that does this annealing, and then it will, we run it under quantum conditions, let it evolve by starting in all spins out, evolving to this one. This is the max 2 sat. This part of the Hamiltonian is the one that made a superposition of all states, and then run it. Now, if you use like D-Wave, they have a free simulator, so you can try using. You don't need to get time on their computer. You can run it on the simulator of their computer and see what happens. You can take problems and plug it in. This is what's going on. When you take a problem and it's you program it, you compile it, you do whatever mapping into the natural language of the machine. It's all about taking these kinds of optimization problems, mapping them into weighted max 2 sat, turning them into a physical control of the machine, executing it, and then seeing what comes out and figuring out what the resources were. So now you understand the whole thing about quantum annealing. And that's the end of my time. So, but any questions anybody has? Any discussion? I'm okay. I don't want to run late. There's another session after this? Yeah, I don't want to. On the last day, if I run over, everything runs over. I'm not going to do that. Anybody? I mean, yeah.
Can we discuss the phase transition from KDL by using this model as Ivy has previously proposed a model?
Yeah, I understand the question. Yeah. So the question here is that, so what he's asking about is phase transitions. So the Ising model purpose really was to explain the phase transition between magnetization and demagnetization. But they were less concerned about individual control. So when you do phase transitions, you're much more interested in global control. You know, you have a non-magnet, you apply a magnet to it. Or you have a magnet and then you heat it up. So the same Hamiltonian applies to the phase transitions, but here we care a lot about controlling individual interactions and weights, and that goes beyond what they were thinking about. So the microscopic control we have is goes beyond that, but there should be phase transition properties, if you fix that. We don't use it to study phase transitions. But so I guess the message is that, when Ising did it, he simplified the physics to that to explain phase transitions. We use the theory he did to explain phase transitions, but for a whole different purpose. Hey, you all get it. Okay.
Going back to an earlier kind of part of the issue, when you mentioned quantum compilers being one of the hot issues, so as a CS community over here, where would you recommend they get started in terms of, after you do your intro quantum class, what should they do?
See, my problem is I don't really know. Like, I do quantum compiling stuff, but I don't know compilers. So you're asking a very good, this is part of the obstacle in the global community, is that people like me who've worked on quantum computing for 25 years are only starting to realize the importance of compilers and the whole architectural stack. And I don't have another year or two to spend learning that topic properly. People who do compilers and architectural stack don't know anything quantum, and they get intimidated by it. I don't know where to link up the two. But I think it's a big opportunity. I think that, like, in the world, there's a shortage of people who know that. We desperately need people to be able to step in and do everything along the way. But you saw, like in my presentations, I'm talking about Trotter formula, I'm talking about graph coloring. So when you start thinking about the implications, if you teach compilers, I don't think you're teaching graph coloring theorems. I don't think that you're teaching operator algebra. I don't think that I don't know, thermodynamic equilibrium is coming in. You see what I mean? So the gaps are so huge. That's why we have a shortage in the world, is because the gap between what computer science and computer engineers learn and what quantum physicists learn is so huge, we don't even know how to fill it yet. Big opportunity and big challenge. Does that help? But if you want to put something together, I'm happy to engage offline.
Where would you recommend someone get started? Let's say if you want to have a course on it.
Well, I guess my view is probably if you get one of the companies to come in. So you had Rigetti talk, they do a bit of it. Microsoft has been doing it for years. Krista Sforti, you know her? So Krista's now promoted to general manager at Microsoft, but she leads the team, the huge team, and like everybody there has to do coding every day, and a lot of the work is about the compiler. They collaborate in Europe with places like Delft and Copenhagen, partly because they want to be using their software with experiments. IonQ, Chris Monroe's company in Maryland, College Park, Maryland, that company is also looking for compilers. They just recently advertised. They're trying hard to hire people. All these companies are writing to me all the time asking if I know anybody, and I say no, nobody there. Then Horizons, Joe Fitzsimon's company, maybe he's interested. So Joe he's in Singapore, and they're hiring, they're specifically going out trying to hire people who could do compiling and know quantum. So just giving you examples. They could give you a rundown of what their challenges are in their strategy. But again, just the short answer is look at Microsoft and go look at do you remember the old Liquid they had? Yeah. Liquid, Solid, and that, and they abandoned it. That was Dave Wecker's stuff. Oh, Dave Wecker. You know Dave Wecker? Yeah, Dave Wecker. If you got him out, Dave Wecker represents to me, in my mind, he's the world's clearest thinker on that whole issue. And he comes from the compiling background. And then about a decade ago, he decided at Microsoft, he transferred, decided to commit the rest of his life to quantum. So he's the guy you want to get. You came to QIP.
Yes.
Dave Wecker gave a session there. Yeah.
Any other questions? It's the last chance.
Last chance.
Thank you.